Hey there, Miss Comfier. This is actually my first video ever, so we're gonna see how it goes. Today I wanted to introduce you to this awesome simulation from the PhET group in Colorado. It talks about microwaves. So we've been talking about the EM spectrum. Here it is again, the EM spectrum. Many different types of electromagnetic waves, and different groups today shared out different uses of electromagnetic waves of these different frequencies and wavelengths. For example, very long wavelengths we use for radio signals, all the way down to very short wavelengths like gamma rays we use for cancer treatment and also for different types of scientific research. But something interesting came up when we talked about microwaves today, and the group who shared out microwaves said that microwaves can be used for, of course, microwave ovens, but then also Wi-Fi, which presumably is all around me at this very moment, many different Wi-Fi signals I can get on my computer here, and cell phones. So how is it that microwave ovens kind of cook our food, and Wi-Fi and cell phones are not cooking my brain or body at this very moment? At least, I hope they're not. Are they? Okay, so how the heck do microwaves work? That's the question for today. So the PhET group in Colorado has this awesome simulation, and here they have a small microwave oven, and inside you can see a bunch of water molecules. These ones are quite cold. They're not even barely moving at this moment. But what we can do is we can choose a frequency of microwave, and that microwave is going to show up with this green line back here, which is just a silly little representation of the electric field. So we know electromagnetic waves oscillate the electric field and the magnetic field. That's why they're called electromagnetic. And so what we're going to see is how when the electric field inside this microwave oven oscillates, how does that affect the water molecules? Because we know fields are around us all the time. So how do they interact with matter? Let's check it out. So we can see that we're oscillating the electric field at a pretty reasonable frequency. In fact, this frequency is very similar to the size of the water molecules, which is actually important. And that it's pausing a little bit, meaning that there's a lot of calculations going on, because these are real-life, real-time calculation simulations. It's not just a video. But anyway, what's happening is we can see that energy is oscillating the field, and somehow the molecules that exist around that field, or the field that exists around the molecules, is transferring energy out of the field and into the molecules themselves, causing them to rotate around and translate and move, and they tend to bump into each other and therefore transfer energy into each other. And as you might have noticed, this thermometer is showing us that the motion of these molecules means that the water molecules are really hot. So we just heated up our water. If you wanted to make tea, you did it. You can also see that I can turn this microwave oven off. And so the green line behind us kind of goes back to normal, meaning we're no longer inputting energy into the field. However, the molecules still have some motion, and they're still able to transfer energy to each other, though they're slowing down over time, presumably because they're radiating energy out of themselves, possibly in the infrared part of the spectrum, and presumably that should actually affect the electric field as well. But over time they tend to cool down, slow down, and stop moving. So that's what happens when our microwave oven turns off. So here's the real question. Why don't Wi-Fi signals do this to our bodies all the time if they're constantly in the field around us? Well, check out what happens if I change the frequency of this microwave to something that's no longer really near the size of the water molecules. So the water molecules are in this simulation about this big, maybe, 1/10 the size of this microwave oven. So what happens if I change my frequency of wave from, you can tell I'm outside. What if I change the frequency from about 3 millimeters? You can see that's 0.003 meters, about 3 millimeters, all the way down to about how low can I get it? How much can I change this? Can I make it 0.03? Well, close enough. 0.00002. So that's about 0.02 millimeters. So about 100 times lower in frequency, which should make our wavelength about 100 times longer. So before, our wavelength was really similar to the size of our water molecules. Let's see what happens when the size of our wave is 100 times longer. So there's our field oscillating. You can barely see it because it's so low in frequency. And you can tell the water molecules, they're getting a little bit of energy from the field, but not a whole lot. And so maybe this is a better simulation of what would be happening in our bodies all the time when we have much longer microwave radiation going through our body and radio wave radiation. So microwave ovens tend to be more like the first wave that we put in. In fact, they're a very specific frequency, and that frequency is basically 2.4 gigahertz, or about 1 millimeter. But this frequency is much more like the Wi-Fi signals or the cell phone signals that are constantly transferring information from our cell phones to the satellites up above. And so this frequency of wave is just not well matched with the size of the water molecules. And so for whatever reason, the size of the wave and the size of the molecule matter. They have to be similar to each other for energy to be transferred from the field into the matter. So you can see that even though these water molecules are getting a little bit of energy, it's nowhere like it was before, and so our temperature gauge really hasn't changed much, and so our body really isn't heating up. So thank goodness, microwaves are just a range of frequencies, and one specific frequency, the one that matches the size of the water molecules, are what we can use in a microwave oven, and other wavelengths, other frequencies of microwave we can use for other purposes, but that won't affect our bodies. All right, Ms. Kumpf, signing off.